For decades, the world of technology has been on a relentless quest to make things smaller, faster, and more powerful. This insatiable hunger for progress has driven us from computers the size of lab rooms to devices that fit in our pockets, each generation outperforming the last. This constant progress has been coined Moore's Law after an observation made by co-founder of Intel Gordon Moore, who stated that the number of transistors on a microchip doubles approximately every 2 years. Transistors are semiconductor devices used to amplify or switch electronic signals and electrical power in circuits. They are like gatekeepers that control the flow of electricity, and the smaller they get, the more powerful our computers become. But as we've squeezed more and more transistors onto silicon wafers, approaching the very limits of miniaturization, a new challenge has emerged. The performance gains we once took for granted have begun to plateau, hampered by the physical constraints of traditional transistor design. Transistors are down to 3 nanometers now, almost the size of atoms, and we cannot follow the Moore's Law forever. This is the challenge facing the semiconductor industry today. Yet, from the fertile grounds of scientific exploration, a new breed of transistor has emerged, promising to shatter these limitations and usher in a new era of technological advancement. This is the story of vertical complementary field effect transistors (VCFETs), a revolutionary technology poised to redefine the boundaries of what's possible. It is like comparing a single-story building and a skyscraper, with its towering structure rising high above the ground, making the most of limited space. Vertical transistors borrow from this simple architectural idea, making full use of our 3D space and flipping the script on traditional transistor design. Instead of lying flat on a silicon wafer, they stand vertically like pillars of conductive material, allowing for greater density and improved performance. This seemingly simple shift in orientation has profound implications, unlocking new levels of efficiency and power. Obviously, by arranging transistors vertically, we can cram more of them into the same area, but the advantages extend far beyond just density per area. Their unique architecture also reduces the distance electrons need to travel, leading to faster switching speeds and lower power consumption. This means our devices could do more, faster, and with less drain on our batteries. Although this idea is rather straightforward, making it a reality turned out to be a major headache. The development of vertical transistors has been a journey of continuous setback, but with a few noteworthy innovations, with the latest breakthrough being published a few days ago in the prestigious scientific journal Nature. Now, let's dive deeper in this work to see what was the issue and how researchers pushed the boundaries of what is possible. A huge roadblock for the development of vertical 3D transistors is about their logic gates. Logic gates in transistors are fundamental building blocks of digital circuits that perform basic logical functions by controlling the flow of electrical signals based on specific rules. Unfortunately, they have always been confined to the surface of the silicon substrate, and no one has ever managed to arrange them into vertically stacked layers. Recently, the use of new materials has been proposed to create the vertical channels. In particular, stacking two-dimensional semiconductors such as MOS2 transition metal dichalcogenides has been seen as the grail in this direction. Yet, to create the logic gates, each 2D layer needs to be precisely controlled to give either N or P-type polarities, that is to say, to have either electron or hole charge carriers. All previous attempts to do this failed, suffering from inhomogeneities or degradation of carrier mobility. Now, authors of the Nature article have achieved it. They report a simple and non-destructive doping method of few-layered transition metal dichalcogenides. This family of materials are usually N-type semiconductors, but authors demonstrated that in contact to antiferromagnetic insulator chromium oxychloride, they reconfigured N-type into P-type semiconductors. This is due to the strong van der Waals interfacial coupling between these two-dimensional materials. Van der Waals forces are weak attractive forces between molecules or materials that help them stick together. And in this specific case of MOS2 and C are OCl, the interaction tuned the properties of this mixture to be perfectly what researchers have been looking for. That is a suitable band alignment, charge transfer, and electron-electron interactions. This breakthrough has not come easy. It's the culmination of years of research and development, countless hours spent in labs by brilliant minds pushing the limits of materials science and nanotechnology. Once researchers understood the mechanism and method to precisely dope MOS2, They then built a vertically stacked transistor, including vertically designed logic gate. With their new method, they can stack as many 2D materials as they want and in the order they want. Here is the logical function NAND, that is A and a no. It takes only a fraction of the surface area normally needed. Amazing! Imagine stacking twice as much transistors in the same space. That could mean a smartphone that's twice as fast, with a battery that lasts twice as long. This is the promise of vertical transistors, unlocking new levels of speed and efficiency. Now, this is exciting, but we are still at an early stage. Authors demonstrated that it could work, but the next question is how to manufacture these at a large scale. This is not clear yet. The method they use to assemble these van der Waals 2D materials is called a dry transfer method, where they manually select and delicately transfer 1 nanosheet at a time. As you can see in this scanning electron microscopy image, nanosheets comes in different size with more or less defects. Not all would work. So the fabrication is still very much kind of an artisanal method, with its success depending greatly on the talent of experimenter. Authors briefly discussed other preparation methods such as chemical vapor deposition, which could be much more scalable, but this is far from being totally convincing yet. We shall see what the future will be. I can only encourage them, and if you like this video and are also waiting for your super smartphone, then click this like button, share, comment, and subscribe to this channel. I am trying to post frequent videos about recent scientific breakthrough. Bye!